50,000 Kelvin. That is almost 10 times hotter than the surface of the Sun, and NASA just confirmed that this is what exists at the edge of our solar system. A wall of superheated plasma that no one predicted, no one expected, and two small spacecraft built in the 1970s just flew through it. They should have melted. They should have fried. Instead, they sent back data that rewrote everything we thought we knew about where our solar neighborhood ends. This is not science fiction. This is measured, confirmed, real, and it changes everything. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. What lies beyond everything we know? Beyond the planets, beyond the comets, beyond the last frozen rocks at the edge of our solar neighborhood. For decades, scientists could only guess. They drew lines on charts. They built models. They imagined invisible walls where our sun is influence faded into the cold, dark of the galaxy. But imagination is not data, and data requires something impossible. You need to send a machine so far from home that it takes nearly a full day for a radio signal traveling at the speed of light just to reach it. You need that machine to survive for decades in the emptiest void humans have ever touched. You need it to keep working long after everyone who built it has retired or passed away. And somehow, against every reasonable expectation, that is exactly what happened. In 2012, a spacecraft called Voyager 1 crossed a boundary that no human-made object had ever crossed. It left the heliosphere. It entered interstellar space. The data it sent back changed everything we thought we knew about the edge of our solar system. And what it found there was not the quiet fade into darkness that scientists predicted. What it found was something far stranger. A wall of superheated plasma, temperatures reaching 50,000 Kelvin, a structured, energetic, turbulent region that rewrote the textbooks. This is not science fiction. This is not speculation. This is measured, confirmed, real. The story of how we got there begins almost 50 years ago. It begins with two spacecraft that were never supposed to last this long. And it begins with a window of time that only opens once every 175 years. September 5th, 1977, Cape Canaveral, Florida. The morning air hangs thick with humidity. On Launch Pad 41, a Titan IIIe Centaur rocket stands fueled and ready. Strapped to its nose is a machine that weighs less than a small car. 825 kilograms of aluminum, copper, electronics and ambition. They call it Voyager 1. 16 days earlier, its twin had already departed. Voyager 2 launched first on August 20th, but it travels a slower path. Voyager 1 will catch up, overtake it, and eventually become the most distant object humanity has ever created. Both spacecraft carry identical instruments, both carry identical gold-plated copper records, and both carry a mission that began as a dream in the minds of engineers who understood something remarkable about planetary geometry. The idea first took shape in 1964. A young aerospace engineer at the Jet Propulsion Laboratory named Gary Flandreau was studying trajectories for potential missions to the outer planets. He noticed something extraordinary in his calculations. In the late 1970s, Jupiter, Saturn, Uranus and Neptune would align in a configuration that occurs only once every 175 years. This alignment meant something profound for spacecraft navigation. A probe could use the gravity of one planet to accelerate and redirect itself toward the next. Slingshot from Jupiter to Saturn, slingshot from Saturn to Uranus, slingshot from Uranus to Neptune. What would normally require separate missions spanning decades and costing billions could potentially be accomplished with a single spacecraft. The math was elegant. The opportunity was fleeting. NASA called the concept the Grand Tour. The original proposal was ambitious. 4 spacecraft, 5 planets, a complete survey of the outer solar system in a single coordinated campaign. But ambition collided with budget. The early 1970s brought cuts to NASA funding. The Vietnam War consumed resources. Public enthusiasm for space exploration had cooled since the Apollo moon landings. The billion-dollar Grand Tour was deemed too expensive. What emerged from the wreckage was something smaller, but still remarkable. The mission was renamed Mariner Jupiter-Saturn 1977. The scope was reduced to just 2 spacecraft visiting just 2 planets. The engineers were told to build machines that would last 5 years. maybe a few more if they were lucky. No one spoke seriously about reaching Uranus or Neptune. No one imagined that these spacecraft would still be operating nearly 50 years later. No one dreamed they would one day touch the space between the stars. Just months before launch, the mission received its final name, Voyager, and the team building it understood they had one chance to get everything right. The Voyager spacecraft are marvels of 1970s engineering, not because they are sophisticated by modern standards. By today's measures, their computers are laughably primitive. Their total memory is measured in kilobytes. A modern smartphone contains more processing power than both Voyagers combined 1 billion times over. What makes them remarkable is their ruggedness, their redundancy, their stubborn refusal to die. The body of each spacecraft is a 10-sided polygon called the bus. It serves as the central hub for all systems. Electronics are distributed across 10 compartments, each serving a specific function: communications, attitude control, data storage, power management, science instruments. The design philosophy was simple. Wherever possible, build in backups. Wherever backups are impossible, build it so robust that failure becomes unlikely. The high-gain antenna is the most recognizable feature, a 3.7-meter dish painted white to reflect solar heat. This antenna must remain pointed at Earth with extraordinary precision. At the distance Voyager now travels, a pointing error of just a fraction of a degree means the signal misses our planet entirely. Keeping that antenna locked on target across decades and billions of kilometers is one of the mission's greatest ongoing achievements. But the true heart of Voyager is not visible from the outside. It is the power source. 3 radioisotope thermoelectric generators, or RTGs, mounted on a boom extending away from the main spacecraft body. These are not batteries. They are not fuel cells. They are small nuclear devices that generate electricity from the decay of plutonium-238. Each RTG contains roughly 4.5 kilograms of plutonium oxide pressed into ceramic spheres and stacked within a housing designed to survive any conceivable accident. The plutonium does not power a reactor. It simply decays, and as it decays, it releases heat. That heat is converted to electricity through thermocouples, devices that generate voltage from temperature differences. No moving parts. Nothing to wear out mechanically. Just the slow, steady, predictable decay of unstable atoms. When Voyager launched in 1977, its RTGs produced roughly 470 watts of electrical power. That is less than a typical household hairdryer, but in the vacuum of space, far from the sun, it is enough. It powers the transmitter, it powers the computers, it powers the science instruments, and it keeps the spacecraft warm enough to function when the surrounding environment is only a few degrees above absolute zero. The catch is that plutonium-238 has a half-life of 87.7 years. Every year, the power output drops. By 2023, the Voyagers were producing only about 225 watts each. NASA engineers have had to make hard choices, turning off heaters, shutting down instruments, conserving every watt for the essentials. The spacecraft are slowly going dark, one system at a time, but they are not dark yet, and the data they send back remains priceless. The original mission plan called for Voyager 1 to make close encounters with Jupiter and then Saturn, with a particular focus on Saturn's giant moon Titan. Titan was known to have a thick atmosphere, a rarity among moons. Scientists were desperate for close observations, but the trajectory required to fly close to Titan would bend Voyager 1's path sharply northward, away from the plane of the solar system. After Saturn, Voyager 1 would have no further planetary encounters. It would simply head outward, into nothing, into everything. Voyager 2 had a different assignment. Its trajectory was designed to preserve the Grand Tour option. If Voyager 1 successfully completed its Titan flyby, Voyager 2 could be retargeted to continue onward. Uranus, Neptune, the ice giants that no spacecraft had ever visited. The dream that budget cuts had supposedly killed might survive after all. Both spacecraft launched without incident. They crossed the asteroid belt without damage. The Pioneers, launched a few years earlier, had proven that the belt was survivable. The rocks that science fiction imagined as dense fields of collision hazards turned out to be scattered so widely that a spacecraft could pass through with minimal risk. Jupiter appeared ahead. the largest planet, a gas giant of swirling bands and ancient storms. Voyager 1 arrived first in March 1979. It passed within 174,000 miles of Jupiter's cloud tops. The images it returned were unlike anything ground-based telescopes could provide. The Great Red Spot, a storm larger than Earth itself, revealed its complex internal structure. Counter-rotating winds, interacting vortices, a system of terrifying power that had been raging for centuries, but the real surprises came from the moons. Io, the innermost of the large Galilean moons, was supposed to be a dead world, cratered and cold. Instead, Voyager discovered a moon literally tearing itself apart. Active volcanoes, plumes of sulfur shooting hundreds of kilometers into space. The tidal forces from Jupiter's immense gravity were heating Io's interior, driving geological activity more intense than anywhere else in the solar system. Europa showed a surface of cracked ice, no impact craters. Something was erasing the geological record, resurfacing the moon. Scientists began to wonder if liquid water might exist beneath that ice shell, if Europa might harbour conditions suitable for life. Ganymede turned out to be the largest moon in the solar system, bigger than the planet Mercury. Callisto was ancient and battered, its surface a record of impacts stretching back billions of years. And Jupiter itself had rings. Faint, dusty, nothing like Saturn's magnificent bands, but present. A discovery no one had anticipated. Voyager 2 followed 4 months later. It confirmed the findings, added new details, and then both spacecraft curved onward towards Saturn. The ringed planet had captivated human imagination since Galileo first glimpsed its strange shape through his primitive telescope in 1610. Ground-based observations had revealed multiple distinct rings separated by gaps, but nothing prepared scientists for what Voyager would show them. The rings were not solid structures. They were composed of countless individual particles, ranging from tiny grains to house-sized chunks of ice and rock, all orbiting Saturn in a flattened disk less than a kilometer thick in places. Voyager's cameras revealed structure within structure, thousands of individual ringlets, waves, gaps, features shaped by the gravitational influence of Saturn's many moons. Some moons acted as shepherds, their gravity confining ring particles into narrow bands. Some embedded themselves within the rings, clearing gaps in their wake. The system was dynamic, interactive, far more complex than anyone had imagined. Voyager 1 made its close approach to Titan in November 1980. The moon's thick orange haze completely obscured its surface. No photographs could penetrate the smog. But the instruments detected nitrogen, methane, and complex organic molecules. Titan's atmosphere was denser than Earth's. It was the only moon in the solar system with a substantial atmosphere, and the chemistry suggested that liquid hydrocarbons might exist on its surface. Lakes of methane, rivers of ethane, a world where organic chemistry was playing out on a planetary scale. The Titan encounter bent Voyager 1's trajectory sharply. After Saturn, it headed north, climbing above the plane where the planets orbit. No more worlds to visit, only the long, slow journey outward. Voyager 2 had its own Saturn encounter 9 months later. Then mission controllers made the call. The Titan data was excellent. Voyager 1 had succeeded. Voyager 2 was cleared for the grand tour. Uranus was 5.5 years away. Neptune was another 3.5 beyond that. The spacecraft that had been built to last 5 years was about to attempt a journey of 12, and after Neptune, it too would head into the void. No one knew what they would find out there. The space between the planets was understood. The space between the stars was theory and conjecture, but both Voyagers were now committed to finding out. On February 14, 1990, Voyager 1 turned its camera backward. It was nearly 4 billion miles from home. At the request of Carl Sagan, the famous astronomer who had helped design the mission's cultural payload, the spacecraft photographed the inner solar system, one last time. The resulting image showed Earth as a single pale blue pixel, suspended in a scattered beam of sunlight. Sagan called it the pale blue dot. He wrote that everyone you have ever known, every human being who ever lived out their lives on that tiny speck. The image became an icon, a reminder of our smallness, and a testament to what that small species had accomplished. The camera was shut down after that photograph. Power was too precious to waste on backward glances. Voyager 1 faced forward now. Its journey was just beginning. What lay ahead was the heliosphere, the vast bubble of plasma and magnetic field that the sun blows around itself. Beyond that was something called the heliopause, the theoretical boundary where the sun's influence ends and interstellar space begins. Beyond that was the unknown. The spacecraft was not designed to explore interstellar space. It was an unexpected gift, a machine that refused to die, heading toward a boundary that might not exist the way scientists imagined. What it would find there would rewrite our understanding of where our solar system ends and where the galaxy begins. And what it found was fire. Chapter 2. The Planetary Grand Tour. The journey from Saturn to Uranus took 5.5 years. 5.5 years of coasting through emptiness. 5.5 years of silence punctuated only by routine telemetry checks and occasional course corrections. Voyager 2 was alone in a way that no human-made object had ever been alone before. Behind it, Saturn shrank to a point of light. Ahead, Uranus was invisible to the spacecraft's cameras, too dim and too distant to photograph until the final months of approach. Mission controllers at the Jet Propulsion Laboratory faced a problem they had never encountered. The spacecraft had been designed for Jupiter and Saturn, worlds that orbit close enough to the Sun that their reflected light is reasonably bright. Uranus orbits nearly twice as far from the Sun as Saturn. The light there is only 1/4 as intense. Photographs taken with the original camera settings would be hopelessly underexposed. Dark smears instead of planetary detail. The solution required reprogramming the spacecraft from billions of miles away. Engineers developed new imaging sequences that compensated for the dim light. Longer exposures, image motion compensation to prevent blurring as the spacecraft swept past. The entire imaging system was essentially rebuilt through software updates transmitted across the void. Commands travelling at the speed of light took 2 hours and 45 minutes to reach Voyager 2. Confirmation that those commands had been received took another 2 hours and 45 minutes to return. Every change required patience measured in hours. January 24th, 1986. Voyager 2 made its closest approach to Uranus, passing within 81,000 kilometers of the planet's cloud tops. What the spacecraft revealed was a world unlike anything encountered before. Uranus rotates on its side. Its axis of rotation is tilted 98 degrees from vertical, meaning it essentially rolls around its orbit like a ball. Scientists still debate what caused this extreme tilt. The leading theory involves a collision with an Earth-sized object early in the solar system's history, an impact so violent it knocked the entire planet sideways. The consequence of this tilt is bizarre seasonal variation. Each pole experiences 42 years of continuous sunlight followed by 42 years of continuous darkness. When Voyager arrived, the South Pole was pointed almost directly at the Sun. The entire southern hemisphere was bathed in permanent daylight, while the northern hemisphere lay in permanent night. Despite this extreme heating asymmetry, Uranus appeared almost featureless, a pale blue-green sphere with none of the bands and storms that characterize Jupiter and Saturn. The atmosphere was cold and sluggish. Methane in the upper layers absorbed red light and reflected blue, giving the planet its distinctive color. But beneath that serene exterior, wind speeds reached over 900 kilometers per hour. The calm appearance was an illusion. Voyager discovered 10 new moons, bringing the total count to 15 at the time. It found 2 new rings in addition to the 9 already known from Earth-based observations. The ring system was dark and narrow, composed of particles that reflected almost no light. Scientists speculated that the rings might be relatively young, perhaps the debris of a destroyed moon. The 5 major moons of Uranus each told a different story. Miranda, the smallest, displayed a surface so chaotic that geologists struggled to explain it. Massive fault canyons, ovoid formations called coronae, terrain that looked like it had been assembled from mismatched pieces. One theory suggested Miranda had been shattered by an impact and then reassembled by gravity, its fragments coming together in random orientations. Another proposed that intense tidal heating had driven dramatic geological activity. The truth remains uncertain. Ariel showed evidence of past geological activity. Umbriel was dark and ancient. Titania and Oberon were larger, cratered, and apparently quiet for billions of years. Each moon was a world unto itself, and Voyager had only hours to study them as it swept through the system. The magnetic field of Uranus added another puzzle. Unlike Earth, where the magnetic poles roughly align with the rotational poles, Uranus has a magnetic axis tilted 60 degrees from its rotational axis. The magnetic center is also offset from the planet's center by about 1/3 of the planetary radius. No one had predicted such a configuration. It suggested that the magnetic field is generated in a shell of electrically conducting material surrounding the core rather than at the core itself. After Uranus, Voyager 2 continued outward. Neptune awaited, 3.5 more years of travel. The most distant planet ever visited by a spacecraft. August 25th, 1989. Exactly 12 years after launch, Voyager 2 made its closest approach to Neptune, passing within 5,000 kilometers of the cloud tops. The timing was not coincidental. Mission planners had calculated the trajectory to arrive on this anniversary. Neptune was not the featureless world that Uranus had appeared to be. Vivid blue, streaked with white clouds of methane ice, the planet displayed a giant storm system dubbed the Great Dark Spot. Similar in relative size to Jupiter's Great Red Spot, it was a massive anticyclonic storm surrounded by the fastest winds ever recorded on any planet. Speeds exceeded 2,000 kilometers per hour. Neptune, despite receiving only 1/900th the solar energy that Earth receives, was geologically and atmospherically active. How could such a distant, cold world generate such violent weather? The answer appeared to be internal heat. Neptune radiates more than twice as much energy as it receives from the Sun. Something inside the planet generates heat, perhaps residual warmth from its formation, perhaps ongoing gravitational contraction. That internal energy drives atmospheric circulation even in the absence of significant solar heating. Triton, Neptune's largest moon, proved to be the most unexpected discovery of the entire Voyager mission. It orbits Neptune backward, in the opposite direction of the planet's rotation. This retrograde orbit means Triton did not form alongside Neptune. It was captured, probably from the Kuiper Belt, the region of icy bodies that extends beyond Neptune's orbit. The capture must have been violent. As Triton settled into its current orbit, tidal forces would have heated its interior dramatically. That heating appears to have resurfaced the Moon relatively recently in geological terms. Voyager found almost no impact craters on Triton. Something had erased the geological record, and then there were the geysers. Voyager photographed dark plumes rising 8 kilometers above Triton's surface. Nitrogen geysers, erupting through the frozen nitrogen ice that covers the Moon. Material from below the surface was being vented into space. On a world with a surface temperature of -235 degrees Celsius, there was still enough internal activity to drive eruptions. Triton became an instant target for future exploration, a captured Kuiper Belt object, a surface being actively reshaped, geysers of nitrogen. Here was a world that demanded closer study. But Voyager 2 could not stay. Its trajectory bent sharply by Neptune's gravity. The spacecraft headed south, diving below the plane of the solar system. Like its twin, it was now on an escape trajectory. Nothing could bring it back. The grand tour was complete. 4 planets, 48 moons, 3 ring systems, countless discoveries that filled textbooks and rewrote scientific understanding. Spacecraft designed to last 5 years had operated for 12, and they showed no signs of stopping. Both Voyagers carried something beyond their scientific instruments. Attached to each spacecraft was a 12-inch gold-plated copper phonograph record, a message in a bottle cast into the cosmic ocean. The idea originated with Carl Sagan. NASA had included simple plaques on the earlier Pioneer spacecraft, drawings indicating the spacecraft's origin and the physical characteristics of the beings who built it. For Voyager, Sagan proposed something more ambitious, a time capsule, a portrait of Earth and its inhabitants, a greeting to any intelligence that might someday find the spacecraft drifting between the stars. The contents were assembled in less than a year. 115 images were encoded in analog form. Photographs of Earth from space, images of human anatomy, Photographs of people eating, drinking, and teaching, children, architecture from around the world, vehicles and tools, plants and animals, a calibration circle to help recipients understand how to decode the images. The audio portion contained sounds of earth, surf, wind, thunder, birds, whales, a human heartbeat, the sound of a kiss, a mother's first words to her newborn child, greetings spoken in 55 languages, from ancient Sumerian to modern Mandarin, a message from the Secretary-General of the United Nations, a statement from President Jimmy Carter, and music. 90 minutes of music from around the world: Bach, Beethoven, Mozart, Chuck Berry's Johnny B. Good, a Navajo night chant, Peruvian wedding music, a Japanese shakuhachi piece, music from Senegal, Australia, Mexico, India, an attempt to convey the breadth of human creativity across cultures and centuries. The record came with a stylus and instructions etched into its cover, diagrams explaining how to play it, a pulsar map showing Earth's position relative to 14, pulsars, allowing recipients to triangulate our location in the galaxy, a representation of the hydrogen atom, using the fundamental constants of physics as a universal language. Will anyone ever find it? The odds are vanishingly small. Space is vast beyond comprehension. Even travelling at 17 kilometers per second, Voyager 1 will not pass within 2 light years of another star for 40,000 years. And that star, a red dwarf called Gliese 445, has no known planets. The spacecraft could drift for billions of years without encountering anything capable of receiving its message. But that was never the point. Carl Sagan understood that the Golden Record was as much a message to ourselves as to any hypothetical aliens. It was an exercise in asking what we would want to say about our species if we only had one chance to speak. It was a statement of hope in a century scarred by world wars and nuclear terror. It was an assertion that we are capable of reaching beyond ourselves, that we can imagine a future where contact between civilizations is possible. The spacecraft will outlast almost everything we have ever built. The pyramids will erode. The continents will drift into unrecognizable configurations. The sun will eventually expand and consume the inner planets. But barring collision with an interstellar object, the Voyager spacecraft will continue drifting through the galaxy for billions of years. They may be the longest-lasting artifacts humanity ever creates. By 1989, both Voyagers were beyond Neptune's orbit. Their planetary missions were complete, but they were still functioning, still transmitting data. And ahead of them lay the boundary between our solar system and interstellar space. The heliosphere awaited, the termination shock, the heliosheath, the heliopause, names for regions that existed only in theory. No spacecraft had ever visited them. No instrument had ever measured what conditions prevailed at the edge of the Sun's domain. The Voyager interstellar mission officially began on January 1st, 1990. A new phase, a new set of objectives. Use the spacecraft's remaining instruments to study the boundary regions of the solar system, characterize the transition from solar wind to interstellar medium, measure cosmic rays, detect radio emissions from the heliopause. No one knew how long it would take. Estimates for the distance to the heliopause range from 80 to 150 astronomical units from the Sun. At Voyager's speed of about 3.5 astronomical units per year, the journey could take decades. The spacecraft would have to survive far longer than they were designed to operate, but they had already proven capable of that, and the engineers who built them had built better than they knew. The long coast toward the edge began. Ahead lay discoveries that would challenge everything scientists thought they understood about where our solar system ends. Ahead lay fire. Chapter 3: Into the Unknown. For decades after the planetary encounters ended, the Voyager spacecraft travelled in silence. Not true silence. Both probes continued transmitting data. Both continued receiving commands from Earth. But the spectacular imagery was over. The close flybys of moons and rings and cloud bands had given way to the monotony of cruise phase. The spacecraft were instruments measuring empty space, counting particles, monitoring magnetic fields, listening to the whisper of radio emissions from regions no one had ever explored. The public largely forgot about them. Voyager faded from headlines. new missions captured attention. The Hubble Space Telescope revealed deep space in unprecedented detail. Mars rovers trundled across alien deserts. The Cassini spacecraft arrived at Saturn and spent 13 years studying the rings and moons that Voyager had glimpsed for only a few days. Space exploration continued, but Voyager receded into memory, a relic of an earlier era still ticking away at the edge of relevance. But at the Jet Propulsion Laboratory, a small team never stopped paying attention. The Voyager interstellar mission had objectives that could only be achieved by patience. The boundary regions of the solar system were still years away. The spacecraft had to survive, the instruments had to keep functioning, the data had to keep flowing. Understanding what Voyager was approaching requires understanding the Sun in a way that the planetary missions never demanded. The Sun is not merely a source of light and heat, it is also a source of wind, a continuous outpouring of charged particles, mostly protons and electrons, streaming outward at speeds between 300 and 800 kilometers per second. This is the solar wind, and it does not stop at the orbit of Neptune. The solar wind carries the Sun's magnetic field with it, stretching field lines outward into space. Together, the solar wind and its embedded magnetic field create a bubble around the Sun called the heliosphere. Everything inside this bubble is, in a sense, still part of the Sun's domain. The solar wind dominates, solar magnetic fields prevail. The environment is distinctly different from the space between stars. But the heliosphere has limits. The solar wind is not infinitely powerful. As it expands outward, it thins. Its pressure drops. Eventually it encounters resistance. That resistance comes from the interstellar medium, the gas and dust and magnetic fields that fill the space between stars. The interstellar medium is not empty. It is sparse by any terrestrial standard, just 1 atom per cubic centimetre or less. But it has pressure. It has its own magnetic field, shaped by the galaxy's rotation and by the remnants of ancient supernova explosions. And it pushes back against the solar wind. The boundary where solar wind meets interstellar medium has structure. Scientists predicted several distinct regions. First, the termination shock. This is where the solar wind abruptly slows from supersonic to subsonic speeds, like water from a faucet hitting a sink basin. The solar wind does not stop at the termination shock. It slows and heats and becomes turbulent, but it continues flowing outward. Beyond the termination shock is a region called the heliosheath. Here the slowed solar wind piles up and flows around the edges of the heliosphere, deflected by the pressure of the interstellar medium. The heliosheath is a turbulent transition zone. Solar particles and interstellar particles mix. Magnetic fields become tangled. The environment is chaotic and poorly understood. Finally, at the outer edge of the heliosheath, there should be the heliopause, the true boundary, the place where solar wind stops entirely and interstellar medium begins. Beyond the heliopause is interstellar space. Beyond it, you are no longer in the Sun's domain. You have left home. These regions existed only in theory when Voyager began its interstellar mission. Models predicted their existence. Calculations estimated their distances, but no measurement had ever confirmed them. No instrument had ever detected the termination shock or crossed the heliopause. Voyager would be the first. December 16th, 2004. Voyager 1 was approximately 94 astronomical units from the Sun, nearly 14 billion kilometers away. The spacecraft detected something strange. The speed of the solar wind, which its instruments had been measuring for decades, dropped abruptly. Particles that had been flowing outward at over 300 kilometers per second suddenly slowed to less than 100. The magnetic field strength increased. The plasma temperature spiked. Voyager 1 had crossed the termination shock. The transition was sharper than anyone expected. Models had predicted a gradual slowdown over millions of kilometers. Instead, the shock was relatively thin, a boundary crossed in hours rather than months. The solar wind went from supersonic to subsonic almost instantly. Beyond the shock, Voyager entered the heliosheath, and here the surprises multiplied. The heliosheath was not the smooth transition zone that simulations had predicted. It was turbulent, chaotic, full of unexpected structure, magnetic fields pointing in unexpected directions, particle populations that did not match models, regions of compression and rarefaction that suggested complex interactions between solar and interstellar material. Voyager 1 sent back data that theorists struggled to interpret. Something was not right with the models. The heliosphere was not shaped the way scientists had assumed. It was not a simple comet-like bubble with a rounded nose and a trailing tail. The reality was more complicated. Meanwhile, Voyager 2 was approaching its own termination shock crossing from a different direction. While Voyager 1 travelled north of the solar system's equatorial plane, Voyager 2 travelled south. If the heliosphere was symmetric, both spacecraft should encounter the termination shock at roughly the same distance from the Sun. If it was asymmetric, the distances would differ. August 30th, 2007. Voyager 2 crossed the termination shock at approximately 84 astronomical units from the Sun. 10 astronomical units closer than Voyager 1 had crossed 3 years earlier. The heliosphere was not symmetric. The side facing the direction of the Sun's motion through interstellar space was compressed. The opposite side was stretched. The interstellar medium was shaping our solar bubble in ways that measurements now confirmed. Voyager 2 had an advantage over its twin. One of its instruments, the plasma science experiment, was still functioning. On Voyager 1, this instrument had failed in 1980. The plasma science experiment could directly measure the properties of the solar wind, its temperature, density, speed, and direction. Voyager 2 could provide data that Voyager 1 could not. The measurements confirmed that the heliosheath was a complex environment. Solar wind slowed to a fraction of its former speed. Temperatures rose dramatically as the kinetic energy of the particles was converted to thermal energy. The transition from inside the termination shock to the heliosheath was a transition from a fast cold flow to a slow hot flow. Both Voyagers continued outward through the heliosheath. The question now was whether they would survive long enough to reach the heliopause itself. Power was declining. Instruments were being shut down one by one to conserve electricity. The spacecraft were aging, their components degrading after decades of operation in harsh conditions. Cosmic rays provided a clue that the heliopause was approaching. Cosmic rays are high-energy particles that originate outside the solar system, accelerated by supernova explosions and other violent events in the galaxy. Inside the heliosphere, the solar wind and its magnetic field provide partial shielding against cosmic rays. The intensity of cosmic rays is lower inside the bubble than outside. As Voyager 1 travelled through the heliosheath, its cosmic ray detectors registered a gradual increase in particle counts. More cosmic rays were reaching the spacecraft. The shielding provided by the heliosphere was weakening. Something was changing. In 2012, the changes accelerated. Cosmic ray intensity increased dramatically. Solar particle intensity dropped. The balance was shifting. Voyager 1 was approaching the edge. August 25, 2012. 121 astronomical units from the Sun. Over 18 billion kilometers from home, Voyager 1 detected an abrupt transition. Cosmic rays jumped to levels consistent with the full intensity of galactic cosmic radiation. Solar particles disappeared entirely. The spacecraft had crossed the heliopause. It had entered interstellar space. Confirmation was not immediate. Scientists debated what the data meant. The magnetic field direction had not changed as much as models predicted. Some argued that Voyager 1 was still inside the heliosphere, merely in an unusual region. But over the following months, additional data accumulated. Radio emissions detected by the spacecraft indicated that it was immersed in interstellar plasma. The plasma density was higher than inside the heliosheath, consistent with interstellar medium rather than solar wind. In 2013, NASA made the official announcement. Voyager 1 had become the first human-made object to leave the heliosphere. For the first time in human history, something we built was travelling through the space between stars. Voyager 2 crossed the heliopause 6 years later, on November 5, 2018. It made the crossing at 119 astronomical units, slightly closer than Voyager 1. The asymmetry of the heliosphere was confirmed again, and this time Voyager 2's functioning plasma instrument could provide direct measurements of conditions on both sides of the boundary. The data from both crossings began to paint a picture of the heliopause that no one had anticipated. The boundary was not a clean transition. It was not a simple wall. It was structured, layered, dynamic, and it was hot. Scientists had expected the space just beyond the heliopause to be cooler than the heliosheath. The interstellar medium, having never been heated by the sun, should be cold. Temperatures of perhaps 10,000 to 15,000 Kelvin. Chilly by plasma physics standards. Instead, Voyager measured temperatures between 30,000 and 50,000 Kelvin, 3 to 5 times higher than predicted. The edge of our solar system was blazing with energy that models had failed to account for. This was the wall of fire, not literal fire, not combustion, but plasma so energetic that its particles moved at tremendous speeds, corresponding to temperatures hot enough to melt steel. The spacecraft were not damaged because the plasma was incredibly thin. Even at 50,000 Kelvin, there were so few particles per cubic centimetre that actual heat transfer was negligible. The Voyagers passed through unscathed, but the discovery demanded explanation. Where was this heat coming from? Why was the boundary so energetic? What was happening at the edge of the heliosphere that no one had predicted? The answers were still emerging. Scientists proposed several mechanisms: compression heating as the solar wind piled up against the interstellar medium, magnetic reconnection events releasing stored energy, shock interactions between different plasma populations. The heliopause was not a passive boundary. It was an active region where tremendous forces collided, and there was more. The magnetic field just beyond the heliopause was aligned with the magnetic field inside. This was unexpected. Scientists had assumed that interstellar magnetic fields would point in different directions from solar magnetic fields. The alignment suggested some deeper connection between our heliosphere and its galactic environment. The cosmic ray data also held surprises. The heliosphere protects the inner solar system from more than 70% of galactic cosmic radiation. This shielding effect was known, but the structure of that shielding, the way cosmic rays increased as the Voyagers moved outward, revealed layers and gradients that models had not captured. Both Voyagers are now in interstellar space. Both continue to transmit data. Both continue to challenge assumptions about the edge of our solar system. The heliopause turned out to be far more complex, far more energetic, far more structured than decades of theoretical work had predicted. This is what happens when theories meet measurement. Voyager showed us that the universe does not always match our expectations, and it showed us that the edge of home is not a quiet fade into darkness. It is a boundary marked by fire. Chapter 4. The Wall of Fire and What Lies Beyond. 50,000 Kelvin. Let that number settle in your mind. The surface of the sun, the blazing disk we cannot look at without protection, burns at roughly 5,800 Kelvin. The wall of plasma that Voyager discovered at the edge of our solar system reaches temperatures nearly 10 times higher. If you could somehow stand at the heliopause and measure the temperature of the particles around you, your thermometer would register conditions hotter than any natural environment in the inner solar system, except the sun's corona. And yet the Voyagers passed through without damage, without overheating, without even noticing in any physical sense that they were surrounded by such extreme energy. This paradox lies at the heart of understanding what the spacecraft found. Temperature in physics is a measure of the average kinetic energy of particles. How fast are they moving? How much energy do they carry? At 50,000 Kelvin, individual particles are moving at tremendous speeds. Protons zip past at hundreds of kilometers per second. Electrons move faster still. By any definition of temperature based on particle energy, this plasma is hot. But temperature is not the same as heat transfer. Heat moves from one object to another through collisions. In a dense medium like air at sea level, particles collide constantly. Touch a hot stove, and trillions of fast-moving molecules slam into your skin every second, transferring their energy and causing burns. But in the sparse environment beyond the heliopause, particles are separated by enormous distances. There might be 1 proton per cubic centimetre, maybe less. A spacecraft passing through this region encounters so few particles that the total energy transferred is negligible. Imagine a room full of bullets travelling at supersonic speed. Terrifying. But now imagine those bullets are spaced a kilometre apart. You could walk through the room and probably never be hit. The individual bullets are deadly, but the chance of collision is almost zero. That is the environment Voyager encountered. Searing hot particles, impossibly sparse, passing through the spacecraft's vicinity without effect. This distinction matters because it tells us something about the physics of the boundary. The heliopause is not a furnace in any conventional sense. It is a region where particles have been accelerated to extreme energies while remaining so thinly spread that their collective effect is minimal. Understanding how those particles got so energetic is the scientific puzzle. Several mechanisms appear to be at work. The first is compression. When the solar wind encounters the interstellar medium, it slows dramatically. The kinetic energy of that bulk flow has to go somewhere. Some of it converts to thermal energy in the particles themselves. The plasma heats up simply because it has stopped moving as fast. This is analogous to how air heats up in front of a supersonic aircraft. Compression converts bulk motion into random particle motion, which we measure as temperature. The second mechanism is magnetic reconnection. Both the heliosphere and the interstellar medium have magnetic fields. When magnetic field lines from different sources come into contact, they can break and reconnect in new configurations. This process releases enormous amounts of energy. The stored magnetic energy converts to kinetic energy in the plasma, accelerating particles to high speeds. Magnetic reconnection is a violent process. It drives solar flares and coronal mass ejections on the Sun. At the heliopause, it may be continuously heating the boundary plasma. The third mechanism involves shock interactions. The heliopause is not a static boundary. It breathes. As the Sun's activity waxes and wanes through its 11-year cycle, the solar wind pressure changes. The heliopause moves inward and outward in response. These motions can create shocks and compressions that further heat the plasma. The boundary is dynamic, and dynamic boundaries dissipate energy. All three mechanisms likely contribute. The precise balance remains a subject of ongoing research. Voyager's data provide constraints, but not complete answers. Future missions will be needed to fully understand the energetics of the heliopause. Beyond the temperature anomaly, Voyager discovered other unexpected features of interstellar space. The magnetic field direction was one of the biggest surprises. Before the crossing, scientists expected the interstellar magnetic field to point in a different direction than the solar magnetic field. The Sun's field is generated by processes inside the Sun and carried outward by the solar wind. The interstellar field is shaped by the galaxy's rotation and by ancient supernova shocks. There was no obvious reason these two fields should be aligned. But when Voyager 1 crossed the heliopause, the magnetic field direction barely changed. The interstellar field was nearly parallel to the field inside the heliosphere. Voyager 2 later confirmed this finding. Both spacecraft found alignment where models predicted divergence. What does this mean? One possibility is coincidence. Perhaps the local interstellar magnetic field just happens to align with the solar field in our particular neighborhood of the galaxy. But scientists are generally suspicious of coincidences. A more interesting possibility is that there is some physical connection, some process by which the heliosphere influences the interstellar medium, or vice versa, maintaining alignment at the boundary. This question remains open. The data are clear, but the explanation is not. Voyager revealed a puzzle that theorists are still working to solve. Another unexpected finding involved the permeability of the heliopause. Scientists had generally assumed that the boundary would be relatively crisp. Solar particles inside, interstellar particles outside. But Voyager found leakage. Some solar particles were escaping through the heliopause, streaming outward along magnetic field lines. Some galactic cosmic rays were penetrating inward, reaching deeper into the heliosphere than models predicted. The heliopause is not a perfect barrier. It is more like a membrane, selectively permeable to certain particle populations. Low-energy particles are generally confined, but higher-energy particles can cross more easily. The boundary filters rather than blocks. This has implications for understanding the heliosphere's protective function. The heliosphere shields the inner solar system from galactic cosmic radiation. This shielding was known before Voyager, inferred from measurements of cosmic ray intensity at different distances from the Sun. But Voyager quantified the effect directly. Inside the heliosphere, cosmic ray intensity is reduced by roughly 70% compared to interstellar space. The heliosphere provides significant protection. That protection matters for life on Earth. Cosmic rays are high-energy particles, mostly protons, accelerated by supernova explosions and other violent events. When cosmic rays hit the atmosphere, they create cascades of secondary particles. Some reach the surface. At high enough doses, cosmic radiation can damage DNA, increasing cancer risk and potentially affecting evolution. Earth has additional protection from its own magnetic field, which deflects charged particles. But the heliosphere provides a first line of defense, reducing the flux before it even reaches the inner solar system. Without the heliosphere, Earth would be bathed in significantly more cosmic radiation. For astronauts traveling beyond Earth's magnetic field, the heliosphere's partial shielding is one of the few sources of protection. Future missions to Mars or beyond will need to account for cosmic ray exposure. Understanding the structure and effectiveness of the heliosphere's shielding is not merely academic, it is a practical concern for human space exploration. Voyager also discovered structure in the interstellar medium itself. The space between stars is not uniform. The local interstellar medium, the region immediately surrounding our solar system, has its own properties and boundaries. Data from both spacecraft indicate density fluctuations in the interstellar plasma. Waves propagate through the medium. Compressions and rarefactions pass by the spacecraft over timescales of months to years. The interstellar medium is not static. It flows, it oscillates. It has weather, in a sense, driven by distant events and large-scale galactic dynamics. Some of these density fluctuations appear to be driven by solar events propagating outward. A powerful coronal mass ejection from the Sun can create a pressure wave that travels through the heliosheath and eventually pushes against the interstellar medium beyond the heliopause. Voyager has detected these delayed signals, solar activity reaching across the boundary months or years after the original eruption. The very local interstellar medium, the region the Voyagers are now traversing, has its own characteristics. It is warmer and less dense than the average interstellar medium. Our solar system appears to be passing through a relatively diffuse cloud of interstellar gas, a region carved out by ancient supernova explosions. The cloud has a name. Scientists call it the local interstellar cloud, or the local fluff. This cloud has dimensions of roughly 30 light-years, and the Sun has been passing through it for perhaps 45,000 years. In another 10 to 20,000 years, we may emerge into a different region with different properties. The interstellar environment is not constant. Over long timescales, it changes, and the heliosphere must adjust. How would a denser interstellar medium affect the heliosphere? The boundary would compress, the heliopause would move inward, the protective bubble would shrink, more cosmic radiation would reach the inner solar system, Earth's atmosphere would receive a higher particle flux. The effects on climate, on biology, on evolution are speculative but potentially significant. This is another area where Voyager's measurements contribute to understanding beyond their immediate scientific interest. By characterizing the current state of the interstellar medium, the spacecraft help us understand how unusual or typical our present environment might be. As of today, both Voyagers continue their journey. Voyager 1 is now over 165 astronomical units from the Sun, nearly 25 billion kilometers. Signals traveling at the speed of light take more than 22 hours to reach Earth. Every communication is a day-long conversation. Send a command, wait a day, receive the response, wait another day, send the next, instruction. The spacecraft are aging. Power declines by roughly 4 watts per year as the plutonium in the radioisotope generators continues its slow decay. Engineers have turned off heaters. They have shut down instruments. They have implemented every power-saving measure they can devise. The goal is to keep at least one science instrument operating into the early 2030s. Eventually, the power will be insufficient to run the transmitter. The last signal will be sent. Earth will listen and hear nothing but static. The Voyagers will go silent, but they will not stop. The spacecraft will continue traveling at roughly 17 kilometers per second. Nothing in space will slow them down. No friction, no drag, just the endless coast outward, carried by momentum imparted nearly 50 years ago. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not stop there. It will drift past and continue into the galaxy. In 296,000 years, Voyager 2 will pass within about 4 light-years of Sirius, the brightest star in our night sky. Again, just a passing encounter. no capture, no destination. The Voyagers will outlast human civilization. They will outlast the species that built them. They will drift through the Milky Way for billions of years, long after the sun expands into a red giant and swallows the Earth, long after the solar system as we know it ceases to exist. They carry the golden record, 115 images, greetings in 55 languages, 90 minutes of music, the sounds of Earth, a message that says we existed. We wondered. We reached. The wall of fire was only the first surprise. What other surprises await in the space between stars? The Voyagers will not tell us. Their instruments are too limited. Their power is fading. But they proved that exploration is possible. They proved that the edge of the solar system is real and measurable and stranger than anyone imagined. Future missions will follow. Plans exist for probes specifically designed for interstellar exploration, faster spacecraft with longer-lived power sources, and more sophisticated instruments. They will build on what Voyager taught us, but Voyager will always be first, the first to leave, the first to cross, the first to touch the fire at the edge of home. Chapter 5. The fading signal. Somewhere beyond the orbit of Pluto, beyond the Kuiper Belt, beyond the heliopause itself, two small spacecraft continue their journey. They are silent now in the sense that matters to most people. No dramatic photographs. No close encounters with alien worlds. Just the steady trickle of data from aging instruments transmitted across distances that make the mind falter. 22 hours. That is how long it takes for a signal from Voyager 1 to reach Earth. A radio wave, travelling at the speed of light, the fastest speed possible in our universe, needs nearly a full day to cross the gulf between the spacecraft and the antennas of the deep space network. Commands sent from Earth take equally long to arrive. Every interaction is a 44-hour conversation. Ask a question. Wait 2 days. Receive the answer. The signal itself is almost impossibly faint. Voyager's transmitter operates at roughly 23 watts, less than a dim household light bulb. That energy spreads across billions of kilometers, diluting by the square of the distance. By the time it reaches Earth, the signal has weakened to a fraction of a billionth of a watt. Detecting it requires the most sensitive radio receivers ever built, giant dishes 60 meters or more in diameter, cooled to cryogenic temperatures to reduce electronic noise. The fact that we can still hear Voyager is one of the quiet miracles of engineering. The fact that Voyager can still transmit is another. Power is the limiting factor. The 3 radioisotope thermoelectric generators that have sustained the spacecraft for nearly 50 years are slowly dying. Not through any failure of design, simply through physics. Plutonium-238 decays with a half-life of 87.7 years. Every year, less plutonium remains. Every year, less heat is generated. Every year, less electricity flows to the instruments and transmitters and heaters that keep Voyager alive. At launch in 1977, the RTGs produced roughly 470 watts of electrical power. By 2023, that had dropped to approximately 225 watts. By 2030, it will be roughly 200 watts. At some point, probably in the early to mid-2030s, the power will drop below the threshold needed to operate the transmitter and even one science instrument simultaneously. NASA engineers have been managing this decline for decades. Their job is to extract every possible day of useful operation from a machine that was designed to last 5 years. It is a kind of triage. Which instruments provide the most valuable data? Which systems are essential for basic spacecraft function? Which can be sacrificed to keep others running? The cameras were turned off in 1990 after the pale blue dot photograph. No point wasting power on images of empty space. Various spectrometers and sensors have been deactivated over the years as their scientific value declined relative to their power consumption. Heaters have been turned off, allowing parts of the spacecraft to cool toward the ambient temperature of deep space. Components designed to operate at comfortable temperatures now function at conditions their designers never anticipated. 4 instruments remain active on Voyager 1. The cosmic ray subsystem, which detects high-energy particles, the low-energy charged particle detector, which measures lower-energy particles, the magnetometer, which monitors magnetic field strength and direction, and the plasma wave subsystem, which detects radio emissions and measures plasma density. These 4 instruments provide the data that make the interstellar missions scientifically valuable. Cosmic rays reveal the radiation environment of interstellar space. Magnetic field measurements characterize the structure of the interstellar medium. Plasma wave data indicate the density and properties of the ionized gas through which Voyager travels. Voyager 2 has a similar instrument suite, with the addition of the plasma science experiment that failed on Voyager 1 decades ago. This instrument provides direct measurements of plasma properties that the other instruments can only infer. It is one of the reasons Voyager 2's heliopause crossing in 2018 provided more complete data than Voyager 1's crossing 6 years earlier. Engineers estimate that science operations can continue until roughly 2030 or perhaps a few years beyond. The exact date depends on how gracefully the power continues to decline and whether any unexpected failures occur. Every year at this point is a gift. Every additional measurement is data that no other spacecraft can provide. When the end comes, it will not be dramatic. There will be no explosion, no final message. The spacecraft will simply stop transmitting. One day, the Deep Space Network will listen at the expected frequency and hear nothing but cosmic static. Voyager will have gone silent, but silent is not the same as gone. The spacecraft will continue traveling. Momentum carries no expiration date. At roughly 17 kilometers per second, Voyager 1 adds about 3.5 astronomical units to its distance from the Sun every year. That velocity will not change unless the spacecraft collides with something, which is extraordinarily unlikely given the emptiness of interstellar space. The journey from here is measured in tens of thousands of years. In roughly 300 years, Voyager 1 will reach the inner edge of the Oort cloud, the vast spherical shell of icy objects that represents the outermost boundary of the Sun's gravitational influence. Crossing the Oort cloud will take about 30,000 years. The cloud extends perhaps 2 light-years from the Sun, a distance that takes even a spacecraft travelling at interstellar velocities an immense span of time to traverse. In 40,000 years, Voyager 1 will make its closest approach to another star. That star is Gliese 445, a red dwarf in the constellation Camelopardalis. Closest approach will still be about 1.6 light-years, far too distant for any meaningful interaction. Voyager will not be captured. It will not orbit. It will drift past as it will drift past every star it ever encounters. The galaxy is simply too large, and stars too widely spaced for collision or capture to be probable. Voyager will wander among the stars for billions of years, long after the Sun has exhausted its hydrogen fuel and ballooned into a red giant, long after Earth has been scorched or swallowed, long after humanity has either transcended its biological origins or joined the countless extinct species that once existed and are now only fossils or memories. The golden record will endure. Copper-plated in gold, protected from cosmic radiation by an aluminum cover, it should survive for 500 million years or more. The degradation will be slow. Cosmic ray impacts will gradually damage the surface. Interstellar dust grains will pit the cover over millions of years, but the record is robust. It was designed to last. If intelligence ever finds it, they will find instructions etched into the cover, diagrams showing how to extract the stylus, directions for playing the record at the correct speed, a pulsar map indicating Earth's location relative to 14 known pulsars, allowing triangulation even after the pulsars have shifted position over millions of years, a representation of the hydrogen atom using the fundamental transition frequency as a unit of time and the hydrogen line wavelength as a unit of distance. Whether any intelligence will ever find it is unknowable. The galaxy contains hundreds of billions of stars. Voyager will pass close to very few of them over any reasonable timescale. The chance of interception by a spacefaring civilization is almost certainly less than 1 in billions. The golden record is more monument than message, more time capsule than communication. Carl Sagan understood this. He wrote that the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The record was never really for aliens. It was for us. An exercise in imagining what we would want to say if we had one chance to speak for our species. An assertion that we are capable of thinking beyond our immediate concerns, beyond our conflicts, beyond our mortality. The contents of the record reflect that aspiration. Greetings in 55 languages, including some no longer spoken. Music from Bach to Chuck Berry to Senegalese percussion. Images of human life in its diversity. sounds of nature and civilization, a mother saying hello to her newborn child, the heartbeat of a woman who would later marry the man who conceived the project, small intimate human moments alongside grand cultural achievements. If you could play the golden record today, you would hear voices of people who have since died. You would see images of places that have since changed. You would encounter a snapshot of humanity from 1977, preserved in analog grooves on a disk, now billions of kilometers from home. The Voyager mission was never supposed to achieve what it achieved. It was supposed to photograph Jupiter and Saturn and then fall silent. The Grand Tour was supposed to be cancelled. The interstellar mission was an improvisation, a refusal to abandon a functioning spacecraft simply because its original objectives were complete. That improvisation led to the greatest distance ever travelled by a human-made object. It led to the first measurements of interstellar space. It led to the discovery of the Wall of Fire. It led to insights about the structure of the heliosphere that reshape our understanding of where our solar system ends. What lessons does Voyager offer? Perhaps that good engineering endures longer than anyone expects. Perhaps that the universe is stranger than our models predict. Perhaps that great achievements sometimes happen not through grand plans, but through persistence, adaptation, and the willingness to keep asking questions even when the answers are decades away. The signal is fading. Every year a little more power disappears. Every year the spacecraft drifts a little farther, but the data continue flowing. The instruments continue measuring, and for a few more years, perhaps until 2030 or beyond, Voyager will keep whispering its discoveries across the void. When the silence finally comes, it will mark the end of direct contact, but not the end of the story. The spacecraft will continue their journey. The golden records will continue their vigil. And somewhere, billions of years in the future, in a galaxy that may look nothing like the one we know, two small machines built by curious apes on a tiny blue planet will still be drifting through the dark, carrying their message, carrying their music, carrying the memory that once there was a species that wondered what lay beyond. If you found this investigation into the edge of our solar system valuable, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments what other cosmic mysteries you would like to explore. The nature of dark matter, the search for extraterrestrial life, the ultimate fate of the universe. Every topic holds stories worth telling, questions worth asking, boundaries worth crossing. These spacecraft are not just machines, they are extensions of human curiosity. They are proof that we can reach beyond ourselves, that we can build things that outlast us, that we can ask questions whose answers take lifetimes to arrive. Voyager crossed the edge of the solar system and found fire. What will we find next? Thank you for watching. I will see you in the next investigation.